So this is the outline of my part. So I'll spend quite some time on the introduction, talking about calibration in forecasting, why we are interested in calibration, what could go wrong when it comes to calibration. I first look at some techniques, which then will be elaborated later on. Then I will talk a little bit about multiclass calibration, why it is special, why it is more complicated, and this is where things are getting really interesting. And then I will summarize and give an overview of the rest of the tutorial, and then hand over to Telmo. Okay, introduction. So calibration is actually an old topic. So it certainly predates me, and I'm an old man, so it probably almost certainly predates all of you. And in particular, weather forecasters start thinking about calibration. So when the weather forecaster says 70% chance of rain, what exactly does that mean? Well, there is, of course, a lot of uncertainty and vagueness in this statement. So, for example, what does rain mean? How hard should it rain before we call it rain? There is uncertainty about temporal aspects. So, raining tomorrow, does that mean it rains the whole day or only a part of the time? There is also spatial uncertainty. These are not the things that we are concerned with. So we assume that rain is a binary thing. We won't talk about the spatial temporal uncertainty. But if a forecaster says 70% chance of rain, it should be followed by rain 70% of the time. And we'll make that a bit more precise. Okay, so this is immediately applicable to binary classification. A prediction, 70% chance of spam, should be actually spam 70% of the time, and non-spam ham 30% of the time. Or in multi-class classification, here's an iris example. A prediction, 70% chance of setosa, 10% chance of versicolor, and 20% chance of virginica should be those three categories in 70, and 10 and 20% of the time. Okay, so in general, we are interested in having a predicted probability or a vector in multi-class cases. We are interested in it matching empirical, i.e. observed probabilities. Okay, so the key word here is X% of the time. How do we operationalize that? Because of course, if I have one forecast from the weather forecaster and he or she says 70% chance of rain, and then it actually rains, should he have said 100% chance of rain? Or if it doesn't rain, should he have said 0% chance of rain? So it's clear that we can't really say that in when we only have single forecasts. Okay, so let's look at a small example. So we have two predictions of 10% chance of rain were followed by no rain. Two predictions of 40% chance of rain had once rain and the other day no rain. Three predictions of 70% chance of rain were once followed by no rain and twice by rain. And finally, one prediction of 90% chance of rain was followed by rain. Is this forecaster well calibrated? And the answer is actually yes, pretty well calibrated. Okay, the two predictions of 10% could have been 0% to match the empirical probabilities. The 40% could have been 50%. The 70% could have been 67%. The 90% could have been 100%. But this only if we take our empirical probabilities very serious, which is of course a bit risky with such a small sample set. So here's the same data in the table. So we have four groups of predictions. And as we already noticed, the 10% chance of rain was a slight overestimate. The 40% chance of rain was a slight underestimate. The 70% chance of rain was again a slight overestimate, and the 90% chance of rain was a slight underestimate. So we can visualize this in what is known in the literature as a reliability diagram. So what we're seeing here on the x-axis are the predicted probabilities. So concentrate on the red pluses for the moment, so there's a lot going on here. So on the x-axis is the predicted probability, on the y-axis is the empirical probability. Okay, so predicted are 0.1, 0.4, 0.7, and 0.9, and empirical are 0, 0.5, 2/3, and 1. So the blue bars are like a histogram, and the red bars shows the miscalibration in a way, because we would be, if we were perfectly calibrated, we would be exactly on the diagonal. Now, I always personally find these plots a little bit misleading, because I always want to make the blue bars higher or lower, but that's what we have under our control, because these are the empirical probabilities. What we really have under our control is move the pluses to the left or to the right. So that's why we see that the 0.1 is an overestimate, because to be on the diagonal, we need to move it to the left. The 0.4 is an underestimate. To be on the diagonal, we need to move it to the right, and so on. Okay? So this is, we will see a lot more of these reliability diagrams, and we will do actual calculations of how we evaluate the quality of these and so on. So this is just to make you aware of some of the issues. So let's now slightly change the predicted probabilities. So I've changed the probabilities now. So in the table on the left, the red bold numbers are slightly changed. And I kept the groupings the same. So for instance, in the first group, the average predicted probability is now 0.15. In the second group, the average predicted probability is now 0.35, and so on. So the diagram has changed a little bit, okay? But of course, there is a question now, where does this grouping come from? So in the previous setting, the grouping was clear, because we only had 4 different predicted numbers, and we put them all in the same group. But now we have 8 unique predicted numbers. So where does this grouping come from? So this is a possible grouping. And if you compare it with the previous figure, you will see that the calibration has got slightly worse. Yeah, so some of the red bars have become a bit bigger. But I could also do a different grouping. I could put the first 4 predictions in one group and the second 4 predictions in the other group. And then actually I suddenly am perfectly calibrated, because the average prediction in the first group is 0.25, which corresponds to 1 in 4 positives. And similarly, the predictions in the second group average to 0.75, and that corresponds to 3 out of 4 positives. Or alternatively, I could just say, no, every distinct predicted probability gets its own group. And then we get something like this. So in this case, if every prediction gets its own group, then the average y is, of course, the empirical probability is always going to be 0 or 1. Okay? So I'm just raising this to demonstrate that actually there is something a bit tricky here. It's not all that straightforward. And this grouping thing, or binning as we will call it, or sometimes pooling, is an essential operation. Yeah, so binning or pooling predictions is a fundamental notion. And we need these bins to evaluate the degree of calibration. Okay, so not just that we need a good set of forecasts or a good set of predictions to make our empirical probability meaningful, but for separate probability values or for similar probability values, we also need enough forecasts or predictions so that we can obtain reliable empirical estimates. So there's clearly a trade-off here. So large bins give better empirical estimates. So for example, if I go back to this one, I have larger bins and I'm a bit more certain about the 1/4 and the 3/4. But smaller bins give me a finer grained assessment. These bins are probably too small. So there's there's one of those trade-offs that we are very familiar with in machine learning, and that really raise empirical issues. There isn't really a clear rule of thumb of how to deal with this. Okay, so that is when discussing evaluation. But what about calibration methods? As we will see, there are binning, putting forecasts in groups, binning them, and then within each group, adjusting the forecast to the empirical probability is also a practical calibration method. So some of these are empirical binning, isotonic regression, which some of you may have heard of, but these are not the only possible calibration methods. Okay, so why are we interested in calibration? Well, in general, to calibrate means to employ a known scale with known properties, right? So we are very used to additive scales, which have a well-defined zero. And there's a whole topic called measurement theory that looks at this. Not all scales are additive. I will get back to this. So for classifiers, we want to use the probability scale. So if all classifiers score on well-calibrated probability scale, then we can use standard decision rules such as maximum posterior probability. Okay. Conversely, if a classifier is poorly calibrated, and we know many examples of those, for example, naive Bayes, then actually the maximum posterior probability decision rule doesn't make sense. Okay, because if the posterior probabilities are poorly calibrated, why would you set the threshold at 0.5? So that's an important reason for calibration. And as I will show in a minute, we can also then adjust these decision rules in a straightforward way to account for different class distributions or for different misclassification costs and still make good optimal decisions. And finally, we can also, if all probability estimators are calibrated, they score on the same scale, and then we can easily combine probability estimates in a well-founded way. So I put a few questions here. Yeah, some of you may have started thinking about this while looking at this slide. When I give this talk elsewhere, I often pause here for audience participation. I'm not going to do that now. Question one, is the probability scale additive? Well, that is actually a tricky question. When do we add probabilities? Well, if we have mutually exclusive events. But much more often, we multiply probabilities, because if we want to, if we have two random events that are independent, then in order to calculate their joint probability, we multiply probabilities. So the probability scale is more often multiplicative than additive. And the second question, how would you combine probability estimates from several well-calibrated models? Well, there would be some kind of averaging involved. And whenever people want to average things, they tend to apply the arithmetic mean. So adding them all up and dividing them by the number of, by how many numbers you have. However, this is, if we have an ensemble of models and we average their scores, this is answering the question, if I uniformly randomly chose one of these models, what is my expectation? What score would that model produce? And that doesn't make any use of the fact that the scores are probabilities. The scores could be anything. So actually, combining probability estimates in a kind of naive Bayes way, assuming that they are independent, and then multiplying them together and either taking the nth root of them or otherwise compensating for the fact that you're kind of overcounting would be an alternative way. So again, I'm just raising this to say, well, there are some non-obvious issues here. But the general point is we want to have calibrated probabilities to do all these things in a reasonable way. So let me talk briefly about decision rules, optimal decisions. So I have some maths on this slide. So there are 3 slides here on this topic. I'm going to go over the maths very quickly. So the idea is that we have misclassification costs. So y hat is j and true y is I. That gives me a misclassification cost. And so the expected cost of predicting class J for an instance is a sum over all true classes weighted by the probability that that true class applies to that instance. So we don't assume 0, 1 cases here. We assume that we have access to the true probability as given by the base optimal classifier. We don't normally have that. So this is a theoretical notion. So all classes, many classes have a non-zero probability to be the true class for this particular instance. And so we take a weighted average over the misclassification costs, and then we predict the class with the lowest expected cost. Okay, so if you take these formulae, they add over the classes. So in a binary setting, we then have 2 classes, so we can write this out. And if you do a little bit of maths, then you will see that on the optimal decision boundary, which is essentially the threshold on the posterior, you have this equation that basically there is this ratio, which is the number between 0 and 1, that gives the optimal threshold on the hypothetical base optimal probabilities. But this is also the optimal threshold if my probabilities are well calibrated. So what you see here in blue is the cost of a false positive minus the cost of a true negative. So making a mistake on the cost of making a mistake versus doing it correctly on an actual negative. Okay, so the cost of a true negative is, of course, it's a negative cost, so the minus sign cancels out. It's often convenient to just set the costs of a true negative and also a cost of a true positive to 0, in which case effectively you get this formula that this ratio C is the cost of a false positive in proportion to the combined cost of 1 false positive or 1 false negative. So there are some examples here. So if the false positive are 4 times as costly as false negatives, then this ratio evaluates to 0.8. Okay, so it makes sense because then we set our threshold, decision threshold higher in order to make only positive predictions if we're really certain. Or we can do something similar with changes to class priors. If we trained on balanced classes, but we want to deploy with 4 times as many positives compared to negatives, and we have lots of positives, so we want to lower our threshold, and we lower the threshold to 0.2. If we have both these things, then these things actually cancel each other out. Okay, we can have both a change in class distribution and also a change in misclassification costs. Okay, so this is one reason why having good probabilities is helpful, because then we have simple ways to change the decision threshold in response to changes in our deployment context. Okay. So I've told you a little bit about what calibration is, why it is important. So let's talk a little bit about common sources of miscalibration. And the most well-known one are underconfidence and overconfidence. Yeah? So underconfidence, a classifier thinks it's worse at separating classes than it actually is. So in the binary case, that means we want to pull predicted probabilities away from the center. For example, the classifier may predict 0.4 if it's actually, for many negative, it may predict 0.4, and for many positive, it may predict 0.6. So we want to, so that's clearly underconfident. We want to pull predicted probabilities away from the center. The opposite thing is actually more common, or quite common at least. A classifier is overconfident. It thinks it's better at separating classes than it actually is. Yeah, so it very often predicts probabilities close to 0 and 1, whereas actually the empirical probabilities are not so extreme. In that case, we need to push predicted probabilities towards the center. And we can have other cases as well, but these are the most common ones. So let's look at these a little bit. So here's an example I found in a well-known paper that is by now an ICML 2005 paper, so 15 years old. So where they studied calibration. So this is now, I took the plot from the paper, but it is essentially each point here is what was the blue bar in the previous in the reliability diagram. So we have 1, 2, 3, 4, 5, 6, 7, 8 bins here, and they clearly, there are distortions. They are away from the diagonal, but the distortions follow a very clear pattern, because this is clearly an underconfidence example. We want to pull the predicted probabilities, which are on the horizontal axis, we want to pull them away from the center. Okay, so modeling this sigmoidal distortion would then give you a calibration procedure. Overconfidence, and here's an example from the same paper with overconfidence, where we see that the points, the distortions are different, and the points need to be pushed towards the diagonal. Now, the solid line that you see here is an attempt at modeling these points as a sigmoid, which clearly is a poor fit, because the sigmoid would be underconfidence, and that's clearly a case of overconfidence here. I think this is actually a naive-based classifier, okay? So in order to correct for this, we need a calibration method that can model these inverse sigmoids. And I'll mention one in a moment that can do this. Okay, let's now have a quick look at some calibration techniques, which will then be expanded on in the third part by Hausong. So we can essentially do this in a parametric or in a non-parametric way. And parametric calibration involves modeling the score distributions within each class. Strictly speaking, we only have to model ratios between those score distributions. So this is sufficient. Modeling the exact score distributions is sufficient, but not strictly necessary. And here Platt scaling is very well known, because that is about converting the scores from a support vector machine, which is geometric distance and not the probability in any sense, converting that to probabilities in a logistic, in a sigmoidal way. And recently, we proposed alternatives to this for classifiers that already score on a 0-1 scale, and this beta calibration and its multiclass version Dirichlet calibration can handle this overconfidence case for which Platt scaling wouldn't work. And then we have other techniques. I already mentioned empirical binning, and there is also isotonic regression, which is essentially the Rock convex hole method, which is also known as the pool adjacent violators algorithm. So let me just say a few words about these techniques. So here is Platt scaling on a single slide. So there's a lot happening on this slide, but as I said, parametric methods model the score distribution. So on the left figure, you see in blue the scores of the negatives, and in red the scores of the positives. Okay, so positive examples tend to have high scores, negative examples tend to have low scores. So from this, we can derive a calibration map, which is the logistic map on the right, which is essentially taking the positive density of the scores and divided by the sum of the positive and the negative densities. And that gives us this logistic monotonic function. This is under the assumption that the two normal distributions on the left, because that's what they are, under the assumption that they have equal variance. We don't have to assume that, but if we assume that they have unequal variance, then our calibration map on the right will become non-monotonic. And then at the bottom, we have essentially the familiar logistic curve, which is 1 over 1 plus e to the power, a linear formula. And the logistic curve has 2 parameters. One is the distance between the means of the 2 normal distributions normalized by their variance. And the midpoint is the mean of means, essentially. Okay, so beta calibration follows the same pattern, but replaces the normal distributions with beta distributions. And this would be useful to calibrate scores from classifiers that already score on a bounded scale, like naive Bayes, for example. So what you see on the left here is 2 score distributions that are very confident. So the red scores for the positives tend to be very high. The blue scores on the left for the negatives are also very extreme as well, a little bit less extreme than the positives, but anyway, quite extreme. So what we need now is a calibrator that is able to make those probability estimates less extreme, and for that we need an inverse logistic map. The procedure is exactly the same. We take the positive density as a ratio to the sum of the positive and the negative density, and that gives us, in this case, in this particular case, an inverse logistic map with essentially the mapping, the formula at the bottom, and this particular curve has actually 3 parameters rather than 2. A and B control, if A equal to B, then we assume that the 2 score distributions are each other's mirror image, but so we can also model asymmetric situations. So we'll come back to each of these, but this gives you a little bit of a taster value, of a taster. And finally, isotonic regression is essentially the ROC convex hull method. I would be amiss if in my talk I wouldn't somewhere mention ROC curves, and here they are. So we have a simple example here. In blue, we have a stepwise ROC curve on the left. In red, we have its convex hull, and the convex hull, if you trace it from the bottom left, you will see it has 1, 2, 3, 4, 5, 6 segments. And those 6 segments are going to be used to perform binning on the scores. I didn't show you the scores here, although they do appear in the rightmost figure, because isotonic regression works with ranks, not scores. But in order to decide what the calibration map is, you have the original scores on the x-axis. So now you get something, it is non-parametric, and you have a piecewise constant calibration map. Okay, and the order of the segments is inverted. So if you look on the right and at the top right segment, that's a segment with calibrated score 1, which corresponds to the ROC curve segment closest to the origin, because there we see only positives. Okay, so here is quite a different but still very useful calibration method. Okay, I need to keep an eye on the time, so let's move on to multi-class calibration. What's so special about multi-class calibration? Well, you could ask the same question about what's special about multi-class classification. And if you are a decision tree person like I am, then I would say, well, there's nothing special. Decision trees can inherently deal with multiple classes. If you're a support vector machine person or a logistic regression person, then you think, well, it's not so straightforward because my method is inherently binary and I need to do some work to apply this to multi-class. And something similar happens with calibration. Some calibration methods are inherently multi-class, but many are not. And that means that when we move from binary to multi-class, we have choices. There are different ways in which we can define multi-class calibration. And so I will briefly talk about 3 possible ways of doing this. In the literature, many recent papers use the weakest of these 3 notions, perhaps not being aware that there are stronger notions of calibration. So these 3 notions are confidence calibration, which only considers the highest predicted probability and ignores all the other ones. We have class-wise calibration, which is essentially a one versus rest type of calibration, considering the marginal probabilities. And then we have full multi-class calibration, which considers the entire vector of predicted probabilities. In 2 classes, all these forms of calibration are equivalent, but for multiple classes, more than 2 classes, they are not, and they become progressively stronger. Okay, so confidence calibration, as I already said, I'm going through this relatively quickly because the mathematics is just there to demonstrate that you can define this precisely. But it's really about here, class I is the most confident class, so I should really have written I star here. So I star is the argmax of the predicted probability. And for that class, we want the confidence, the predicted probability, to match the empirical probability. Okay, so that's one option. A much older notion of class-wise calibration is basically saying that all one versus rest binary probability estimators are calibrated. So that's a stronger concept because we're not only looking at the argmax, we're looking at all of them. And finally, we can look at the whole vector of predicted probabilities. In each case, want to make sure that that vector of predicted probabilities matches the vector of empirical probabilities, and that is written on this slide. And the confusing thing sometimes in the literature is that people just talk about calibration and they are not always clear which one of these they mean. So these terms are our way of distinguishing between them, and this is what we will use in the tutorial. And just to remind you, and this will come back a couple of times during the tutorial, these are kind of theoretical definitions. So all these formulas have an equality. So the empirical probability equals the predicted probability, either for the whole vector or marginal or for the argmax. But of course, this equality needs to be relaxed, and that is where binning comes in. Okay, so and once we have the bins, we can draw a reliability diagram as in the 2-class case. So for class-wise calibration, we can either show a reliability diagram for each class separately, or we can average all of them. For confidence calibration, we by definition have only a single reliability diagram, but this kind of mixes the classes because it only looks at the most confidently predicted class. And the degree, as before, the degree of calibration is assessed using those gaps, the deviations from the diagonal in the reliability diagram. So again, this will be elaborated in Telmo's part after this part. Okay, so let me summarize and then leave hopefully some time for questions. Okay. So this is not actually a summary. These are just some points that I want to emphasize. Only well-calibrated probability estimates are worthy to be called probabilities. I don't think naive Bayes is actually a probability estimator. It's a scoring classifier that happens to score in the 0-1 range. That's all you can say about it. And calling them probabilities is really an overstatement. Okay, secondly, binning will be required in some form. And so sometimes people evaluate their probability estimates by an instance-based yeah, by a sum or an average over all instances. That is quite common. You have Breyer score, which is mean squared error, essentially. You have log loss, but these always measure calibration plus something else. And this will be elaborated in the next part. And in multi-class settings, it is really important that you think, before you do anything, that you think about which kind of calibration do you need. So, for example, if you imagine that your misclassification costs are going to change, then just doing confidence calibration is too weak because it won't give you optimal decisions. Okay, this is what's going to happen next. So we have the second part after this one, then we have a short break. Then we have House Song talking about calibrators. We have Miquel doing the hands-on session. And then finally, House Song and me come back to conclude things. And we should be done by 6 p.m. Continental time. Okay, and there are some references here. So this material will be made available on the tutorial website, and there are some acknowledgements here as well. So let me stop here, and maybe one of my co-presenters can let me know if there are any questions that I should answer.
Thanks, Peter, for the nice introduction. So if any of you have questions, please just put in the chat channel for now. I think we have probably time for one question. Or let me make a start. Peter, so basically you give us, so your title is what and why. So I'm rather interested, can you give us some real scenarios where you think you don't really need to consider calibration at all, or there's any particular scenario you think that calibration is something that we must have?
Thanks, Hal. There are actually some questions coming in, so have a look at that while I answer this one. This almost looked like a planted one, but it isn't, I promise. So actually, I have an answer to this in the final part, but very briefly. If you are confident that posterior probability 0.5 is always the right decision boundary, you only need to care about where that, you only need to calibrate that decision boundary. But that would require that your class distribution never changes, that your misclassification costs never change, right? So if that isn't true, then you need to care about calibration. If your class distribution might change, if your decision boundary might change, if in future you may get a second classifier and you need to combine the predictions from different classifiers, then you need to worry about calibration. There's a few there's a few questions in the chat. Maybe you could pick one or two of those.
So yeah, I think we have two. So one of the questions is that, can you envision a calibration in a scenario where you only have a subset of the labels that is potentially biased?
Okay, interesting. I think there is a link here to possibly positive only learning, where you have your examples that are either unlabeled or positive, and you can do something there. It's a good question. I don't have a direct answer to that. I don't know if any of my co-presenters want to comment on this, but it's a good question, and I don't think it's a solved issue.
Okay, thanks. So we had, given the time, let's have another. So is there a version of multi-class classification for the numerical case?
Okay. So where you are predicting a vector of numbers, I'm guessing. For the numerical case, so regression, so if you're predicting a single regression, a single number, then actually how we'll talk about that in the advanced topics. So calibration also arises in that setting. Multi-output regression, that should be some kind of generalization of that. But essentially, what is the difference is that in classification, let's say in binary classification, your target is a Bernoulli variable, and you want to quantify your uncertainty in that Bernoulli variable. So that's really what calibration is about. In the regression case, your target is a real number, and you want to quantify your uncertainty in that real number, for example, by modeling it as a normal distribution. So if you have multi-output regression, you would presumably have multivariate normal distributions. And by the way, while I'm saying this is not an answer to that question, but on Friday, there is a tutorial and a workshop on uncertainty in machine learning. I'm not directly involved in the workshop. I think I was on the PC, but it's not something that I'm organizing. So the relationship between calibration and uncertainty is that calibration only talks about the uncertainty in the prediction, okay? So for example, if I toss a coin, I will be, and it's a fair coin, I will be maximally uncertain about whether the coin comes up heads or tails, but I will be very certain that the 50% probability of it coming up heads is the right probability. So uncertainty manifests itself at different levels. And here we're only talking about the uncertainty in the target variable, whereas if you have the wider perspective of uncertainty, you can also talk about the uncertainty that you have in your calibrated probability, which would be very high for a coin toss.